So last time we were talking about hydrostatics, where the acceleration is zero, usually just a fluid that's sitting there not moving. And what we found was that the pressure only depends on the depth of the fluid at that point that we're looking for the pressure, and some fluid properties, which actually has to do with the weight of the fluid. So you could also write this as plus or minus gamma, where gamma is rho g, that's called the specific weight, newtons per meter cubed, times the absolute value of delta z. Okay, that is equal to the pressure difference. Okay, so what we're going to do now is a few applications of hydrostatics. And the first one is manometers. And manometers are pressure measuring devices. They're very simple, and that's why they're great. And they're pretty accurate too. They're so simple actually that you can easily build one yourself. And what it does is use this hydrostatic principle in order to measure a pressure difference. Okay, so for instance, we have a figure here. There's a tank filled with oil. And let's say we want to measure the pressure there at 1 in this sealed tank. Well, what you can do is just attach this, it looks like a U-tube manometer to it. This happens to be filled with mercury. Mercury is a good fluid to use for a manometer because it's very heavy, so you can measure large pressure differences with mercury. The problem with mercury, though, is that it's toxic. So in the past, a lot of our manometers were made with mercury, but not as much these days. But you'll still find them around. So you just have to be careful with them. So anyways, this is what your manometer looks like. And just by knowing what these heights are, we're going to be able to tell what the pressure is at 1 in the tank. Okay, and we've already gone through the solution procedure last time, but let's go through it again. Basically what you do is you label the start point where you want to find the pressure in this case, and every interface with different fluids. Okay. In actuality, this particular figure has a few extra points. This point, not needed. If you think about it, so you're in the oil and you're going to go down in depth, so pressure is going to go up, 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 up. Now we hit mercury. Pressure is still going to go up, up, up. In fact, it's going to go up a lot through the mercury. Up, 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 up. Go across, same, 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 same. Down, 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 down. Back to the same exact pressure that we had at 2. So you don't really need that B. And then from there, the pressure is going to go down, 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 down until we get to the top. So pressure goes up as you go deeper, goes down as you go higher. All right, so what you do, it's the same as last time. You label all your interfaces and where you want to find the pressure and any known pressures as well. And then you just start working your way around writing the hydrostatic equation for each section of fluid. So here we could either start at 1 and 1 to 2 and 2 to 3, and in this case 3 to 4. We don't really need 4 as well. And the reason we don't need 4 is because this is a gas, and in a gas we assume that P3 here is going to equal P4, right? Constant in a gas, if you remember that from last time. All right, so what we're going to do is go work our way around, and we can start at 1 or we can start at 3, either way. Here I started at 1 and I did P2 minus P1. It really doesn't matter which way you go. P2 minus P1, okay, equals rho, so you got to have the fluid that's in between 1 and 2, rho of the oil times G, could also use gamma for the oil there, times the vertical distance. And it doesn't matter if you went sideways. Remember, it's constant, constant, constant pressure whenever you go sideways. So this 9 centimeters. And 2 is below 1. So if you write P2 minus P1, 2 has a higher pressure. So that's going to end up being positive. So you can just leave that as a positive. Okay. If we'd written P1 minus P2, we would have put a negative sign there. All right. The next one, P3 minus P2, is going to be the fluid in between, which is rho of the mercury times G, or gamma of the mercury, times the vertical distance between 2 and 3. This part doesn't matter. We don't even need that. Because, like I said, pressure goes up, 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 then right back down, down, down. So that part doesn't matter. It doesn't matter how deep that manometer goes there. So plug that in, and we know P3 is above P2. All right, so this is going to have a lower pressure than 2. So we're going to have a minus sign in there. So the next thing you do is just add these two equations together, and the nice thing is all your intermediate pressures cancel out. So you're going to get P3 minus P1, and then you just add together the right-hand side. And noting that P3 is open to the atmosphere, so that's going to be P atmosphere. We can plug that in. P atmosphere for metric is about 101,325 pascals. All right. From table 2.1, we're going to get our gamma for our water and gamma for our mercury. Plug all those numbers in, and we're going to end up with P1 is 128,590 pascals. Okay, and I got that by putting a P atmosphere in here for P3. Another thing I could have done was said, oh, I'm going to just use gauge pressure. Since all these are subtractions of pressures, we could just use gauge pressure, and P atmosphere would be 0, and then our answer, P1, would have been in gauge pressure instead of in absolute pressure. So, but what we got was 128.6 kilopascals, which is higher than P atmosphere. What you want to do when you finally come up with an answer is to check your signs. So if you look back up here, does that make sense that that was higher than P atmosphere? And yeah, it kind of does. P2 is definitely higher than P3, which is P atmosphere. So this is a high pressure here. Now P1 is less than P2 because it's higher, but it takes a lot to move this mercury, so it makes sense that P1 is also higher than P3. So that kind of makes sense. So that's a good thing. A few notes here. Manometers, nice and simple. As long as you know what fluid you have in there, you can look up their densities or their specific weights, and you just need to know the distances in order to do this. And it's a simple process that you can do every time. Just write the equations and add them together. P atmosphere isn't always the same. We use that 101 kilopascals, but it changes. Are you on the mountaintop, or you're down in Death Valley, or it just changes day by day. In order to get the actual P atmosphere, you can use a barometer, and a barometer could be a manometer with a vacuum on one side of the manometer, and that would give you atmospheric pressure using the same equations. Also, if we know these tank dimensions back here, if we knew these tank dimensions, and once we had P1 here, we could figure out what the pressure was at any place inside that tank because the fluid's not moving. All right, let's do another example. So we've got a pipe, and a mercury manometer is connected to 2 points in the pipe, and we're given a manometer reading of 55 centimeters, and we're supposed to find the pressure drop between the 2 points. So what we're going to do is our method that we just had. Okay, so the first thing is label all of your interfaces and all the points where you know the pressure, all where you want to find the pressure. In this case, what we're trying to find is the pressure drop between the 2 points. These are the 2 points. We're trying to find P1 minus P4. Okay, that's a pressure drop. So what I'm going to do here then is start at 1 and work my way around to 4. Okay, we already have this L in here. It doesn't give us a number for L, but it turns out we're not going to need a number for that. If you weren't given L and you don't know what a distance is, just go ahead and make up a letter, put in a variable. And that works. A lot of times what's going to happen is things going to cancel out. If you look at this side, you've got water, and you're going to go a particular distance, and over on this side you're going to go that same distance through that same fluid. Things are going to cancel out. Okay, so let's go ahead and do our little method here. So we're going to start with P1, and we're going to go to P2, and in between is water, gamma, water. And this distance, well, from 1 to here is half of d over 2. From here to here then is L, and from here to here is h, which actually is given. I'll just leave it as h. So now from 1 to 2 we need to figure out, is this positive? Is this difference positive or negative? Well, 2 has to be bigger than 1, right? The pressure at 2 is bigger because we're at a higher depth. So 1 minus 2, well, that must be negative. All right, let's do 2 to 3. Okay, this is mercury. The fluid between 2 and 3, mercury. Symbol Hg. And the distance is just h. Okay, 2 is at a bigger depth than 3. Okay, so therefore 2 minus 3 must be positive. Okay, let's do 3. P3 minus P4. Okay, water. And what we have in here is L plus D over 2. All right, and 3 is deeper than 4, so 3 has a bigger pressure, so again, we got positive. All right, add these together. All the intermediate pressures cancel. P1 minus P4 is what we're looking for. And what we're going to get is water, or let's put this in terms of gamma water here. We have that in every term because a lot of times what we'll do is use specific gravity. So I happen to remember that specific gravity of mercury equals 13.8, or 13.6, sorry, which means that gamma for the mercury is 13.6 times gamma of water. So now I have gamma of water in every term, and then I have an H here. All right, so gamma of water, I'm going to pull that out of every term, and if I pull that minus sign in, minus D over 2, minus L, minus H, down to the next term, plus 13.6H, down to the next term, plus L, plus D over 2. Okay, so simplifying, voila, D over 2's cancel, L's cancel, nice. So your P1 minus P4 is going to be gamma of the water times 14.6 H. Well, H is 0.55 meters. Comes out to 67.8 kilopascals. Where gamma of water, let me write that up here, gamma of water for metric, 9790 newtons per meter cubed. All right, go ahead and do questions 1 through 3 from the notes quiz.